Okay. So we talked about all matrices that preserve the inner product, all right? And this is upon transforming it. And this happens when these vectors transform under this rule. And this happens when lambda as a matrix satisfies the following property. Please check if this is correct.
Yeah.
What we will need today is an expression that I'm going to use. This guy, I'm going to write it on the top corner there. This guy in matrix notation, like matrix multiplication, reads like this, alpha, beta. It's in your notes. Lambda mu, lambda mu alpha, lambda mu beta. That's what I'm thinking. Let me see. Mu beta. Yeah, it's when I raise the indices, it becomes, in this one, I had given to you as, it's proved in my notes, but I've asked you to read this on your own because it's very similar to that. Mu beta. This is just a, this index raised version of that. We'll hang on to that. And the set of all lambdas that satisfy this is called what? General homogeneous Lorentz group. And it's denoted by script L. We also know that determinant of lambda is what? Plus or minus 1. Okay. That is where we are so far. So this will help us define the direction of future to some extent. So in my notes, so I'm going to upload my edited notes today so that these numbers will be consistent. I have asked you in problem 2.8 to show that this is a group. We talked about this. And when I say this is a group, what does it mean? The identity is a Lorentz transformation or the member of the general homogeneous Lorentz group. The inverse exists, and product, when you multiply two such lambdas, you get another lambda in the same set. And this you can, it's easy to verify. Now, theorem 2.9 says the following. Lambda 0, 0, so that is the top left corner element, squared equals 1 plus I equals 1 to 3. Now you wonder why I'm doing that. Obviously because lambda, k. K equals 1 to 3. Or I can even write it as 1 plus k equals 1 to 3, lambda 0 k. Okay? That's the theorem which I have to prove. You would think, well, it's an odd thing to prove. Question is, why are we proving it? But there's a reason. So what I'm going to do is take this equation and replace alpha and beta with 0 and 0. So I have negative 1 equals 1, 0, 0, right? Because the 0, 0 element of eta is what? Negative 1. So that's going to be equal to, so every time so this will be, if I just write that down, I get alpha, beta, no, this is mu. sorry, mu nu, mu alpha, nu beta. Hold on, I'm going to erase this. I just picked alpha and beta to be 0 and 0. So 0, 0. Well, thankfully, this is, and this is again a good way to see Einstein's summation convention, right? So I'm going to write it out explicitly. When I do, I'm going to get the result on the top.
Sum over mu and sum over mu.
Sum over mu and sum over nu. So the first non-zero element is 0, 0. But lambda eta 0, 0 is minus 1. So minus 1, lambda 0, 0, lambda 0, 0. The next one is, you can see where we're going with this. Lambda 1, 0, lambda 1, 0, plus lambda 2, 0, lambda 2, 0, plus lambda 3, 0, lambda 3. I just wrote it without your matrix summation. So I get minus 1 equals minus lambda 0, 0 squared plus k equals 1 to 3 lambda k 0 squared. And this is nothing but that. Bring all the negative sides to the opposite direction. So, but another point is, here I have to put an explicit summation. Because if I put lambda k0, lambda, because it's squared, k0, it's not a repeated index up and down. So I don't have that rule that we can use. And we have to stick to it, otherwise if we keep breaking it, then, you know. Yeah. Now, what I won't do is the second part, but you tell me, how will I show the second part? If you were to guess.
Pretty much the second there.
Where are you going to start? It is pretty much the same way. The answer is on the board.
You'll start with mu.
Correct.
Mu nu on the top.
Correct.
And go the other way around.
Yeah. So this time, if you let nu to be 0, 0, the other one works out. The point, so the proof is over. The point is lambda 0, 0 squared is greater than or equal to 1. Which obviously means two situations, which means lambda 0, 0 is greater than or equal to 1, or lambda 0, 0 is less than or equal to minus 1. Correct? Because when you square it, it has to be greater than. So no, lambda 0, 0 cannot have values between minus 1 and 1.
Just to hammer it down real quick. Eta to the mu nu up is technically considering the inverse.
Inverse, correct.
And that's always going to be implied whenever it's on the top. Right?
Correct. Only for eta. Yeah? If I write any other matrix or vector, well, for a vector that doesn't even make sense to have an inverse. But you can have two indices with 2 up, and same thing with 2 down does not mean that they're inverse. Only for eta.
Only eta, but then eta's inverse is just
Eta.
okay.
Too many etas.
Yeah.
Okay, so using some, let me state this. Are you guys working on the problems?
Yeah.
Yeah.
Working through.
So the problem say, again, I'm not going to do this because it's a problem. An element of the Lorentz, homogeneous Lorentz group is a rotation. If and only if lambda 0, 0 equals 1. Meaning, if it's a rotation, don't mess with the time component. Makes sense. this is definition 2.5. If lambda 0, 0 is greater than or equal to 1, lambda being a homogeneous Lorentz transformation. Again, the precise sentence is in the notes. In that case, we will say lambda is orthochronous. One could choose to pronounce it differently. N-O-U-S. And if lambda 0, 0 is less than or equal to minus 1, lambda is what? Non-orthogonous or orthogonal. That's just a label. But obviously, we're going to start defining what keeps future pointing. That's where we're headed. This is the interesting part. Somehow, things are getting special. The set of all orthogonous NOUS elements of L forms a subgroup. What does subgroup mean? It means it's not all of L, but those elements whose lambda 0, 0 is greater than 1 is a group by itself. So if you have an element in that group, its inverse is also in that element. So the inverse matrix will also have lambda 0, 0 to be greater than or equal to 1. And if you multiply two of them, you're going to again get the same thing. So here's the proof. Now what we're trying to do, we're going to find all Lorentz transformations that will not flip the direction of time. And say these are the only things that will allow for physics to happen. So that it looks abstract at the moment. Okay? But that's where we're headed. So what I'm going to do is the following. I'm going to take two lambdas that belongs to the non-orthogonous group, right? Subgroup. Well, we don't know if it's a subgroup. Two orthogonous elements of the general homogeneous Lorentz group. Then I'm going to multiply them. And I'm going to do this. And I want to show this is greater than or equal to 1. Well, what is that equal to? Think of it as I have my things, and I'm going to multiply them. 0. This is lambda 0, 1. This is lambda bar 0, 1. So if I want to get this element, I take this row and multiply. Right? There are 4. I can write all of them. So I'm going to go through this list, and I'm oops. First of all, is this correct?
The math is, but I'm confused with your notation.
Oh, Okay, good. That's not good. That's clear.
Good, let's
Good
continue.
little penitentiary.
Yeah. Sorry.
Good
Sorry.
little penitentiary.
Yeah, so why have you labeled it as if the lambda bar is a transverse?
No. No, good question. These guys have 16 elements. These guys have 16 elements. Right, but I'm only concerned when you multiply, I'm only concerned about the result 0, 0 component.
Yes.
The 0, 0 component is obtained by multiplying like this.
But in that case, wouldn't your summation be lambda 0I with lambda bar I0?
Lambda 0I, lambda bar 0I.
Yeah, but why, that's where I'm confused. Why is your notation going down the
Ooh!
row having that? Shouldn't it be
Yeah.
1, 0?
Yeah,
Okay.
Lambda.
Just because like matrix notation in
Very
general
good.
usually is 1,
You are
0.
confused because you are correct.
Okay.
Yeah. So I should fix that in my notes. Hey, does that mean we don't have to put the summation symbol?
No.
Yeah, it is. We do, but it doesn't have to go to the 0th
Yeah.
element
Yeah.
because the 0th element is over here. And it's understood that I goes from 1 to 3, mu nu alpha goes from 0 to 3.
Oh, because
Yeah,
it's not
that's-
mu, we can just remove the summation symbol.
But we cannot do the 0 here.
Well, but if you remove it because it's not mu, because it's I.
Yeah,
it's
it would work. It would work.
Gotcha.
So let me make sure that is absolutely correct. So I need to fix that in my notes. Okay, but we know what this guy is from the result before that I just erased. They're both orthogonal, so it is positive. It is 1 plus lambda 0k squared, 1 plus lambda bar k0 squared. See, I'm using 0k for one, k0 for the other, and plus I'm so glad you caught that, Jackson, because, you know, in this notation, one is just inclined to say, yeah, that sounds about right, and move on. But look at this. What we want to show is this is greater than 1. What is this? This is like, at the end, it's 3 pairs of numbers that are multiplied, correct? That's like A dot B. Right? The most A dot B is what? Most A dot B it can be is less than why is that true? Because it's actually A law of cosine. Very good. Magnitude of A times magnitude of B times cosine theta. Yeah. So cosine has a maximum of 1. So it's going to be less than that. So I can write, I think my use for this is over. If not, oh no, it's not over. But I'll keep it 1 plus 0k squared, 1 plus k0 squared minus, oh, I'm going to say this guy is greater. This is plus, and I'm going to write the maximum magnitude of what this is going to be. Isn't that true? This is like the magnitude of this is that. This is the magnitude of that.
Should it be less than that?
No, that's greater because I subtracted the maximum value.
Oh, you're subtracting the maximum value, so it
Yeah.
becomes greater than.
Yeah, it can only be greater because, yeah.
I see.
Well, now all you have to do is stare. This number is bigger than this. This number is bigger than that. And they're all positive. So when you subtract a smaller number from a bigger number, you're going to get and that's actually enough. It's actually bigger than 1. Let me see how I wrote it in my notes. Yeah, but we don't, at the moment, we don't care. Because we know it's a group.
It has to be bigger than 1.
So it's either bigger than 1 or smaller than minus 1. But all we have to do is show that it's positive. So it has to be bigger than 1. Therefore, if I take 2 elements of an orthogonous general homogeneous Lorentz transformation, I get another one of the same thing back. Oh, almost. Well, if I multiply 2. What about the inverse? Thankfully, we have the formula for an inverse, right? And let me put that over here. So if I want, what is the inverse of this? Lambda of mu nu, correct? We just showed that. So lambda, I only care about the 0, 0 element, is equal to eta 0 alpha, and then eta 0 beta lambda a, oh, alpha beta. They're both 0, so only time this can happen is when alpha and beta is 0.
That's greater than or equal to something.
Well, yeah, because the original lambda is orthogonous. Zachary, how are we doing? You know, we'll be plowing through just not difficult material, but lots of it, and it's abstract. So let's pause for 10 seconds for questions. I'll let you copy this first. What are your thoughts? So what we have shown, for some reason, lambda, the 0, 0 component, the top left component, if you will, has to be greater than or equal to 1 in magnitude. It can be greater than or equal to 1 or less than or equal to minus 1. Why? We don't know. I'll just show. Fine. The next thing, we're taking to the trouble to show you that this forms a subgroup. What does that mean? It is a subset of the original big group, but that is also a group in and of itself, right? So inside a big bag of this general homogeneous Lorentz transformation, there's a smaller bag. And as long as you stay in that bag, you live in that bag.
I do have a question, actually.
Yeah.
You mentioned how lambda being orthogonous makes it possible for us to do physics.
Correct.
Does that mean that if lambda is non-orthogonous,
Yeah.
it breaks the laws of physics?
Yes, it makes copy of that.
Yeah, it makes like tachyons or something like that. Right?
Okay.
Yeah, we'll see. We'll connect it.
But also the fact that we said that this lambda forms a subgroup
Yeah.
implies that the other one might not.
Correct.
So because if you multiply 2 of those together, we
Yeah.
end up getting one
Yes,
of these.
you could get one of these.
Okay.
Yeah, it's kind of weird, right?
I mean, it kind of makes sense, because like if you multiply 2 negatives together, you're going to get a positive, but if you multiply 2 positives together, you'll never get a negative.
Correct. But it's amazing how causality is tied into it, and every single time in life, math just works out. Like nature had previously conversed with math. and said, well, we have a deal.
Yeah. So, or we just interpret nature as math.
Yeah, yeah. It's just realization of theorems, no? A little bit of notation. And you'll love this. This is kind of fun. I hate to write all of these down. It's just long words. So, I don't know. There's a word for it. So L, the script L with a subscript. So this is all the lambda in L such that determinant of lambda equals 1. What do you think this is?
All lambdas were determined as -1.
Yeah. Check this out. I don't know how to pronounce this. I'm just going to have to say plus arrow up, plus arrow down. Again, these are not difficult problems, but I want you to do this. Problem 2.10. Show that there's nothing much to show. We already have shown that if it's orthogonal, it's a subgroup. This is a
Subgroup of a
subgroup of a subgroup. This is the one that we care the most. This is all the lambdas such that its determinant is 1 and the 0, 0 element is greater than or equal to 1. We have refined lambdas to everything we want.
How is it possible to get a determinant of 1 but have lambda be less than or equal to 1? Or lambda squared be less than or equal to 1?
Not lambda.
Sorry, yeah, just lambda 0, 0.
0, 0.
How can you have lambda 0, 0 be less than 1 with determinants to be 1?
Oh.
Oh, yeah, okay.
I don't know.
One of the other ones.
Yeah, I don't know if this may not be a homogeneous Lorentz transformation, I don't know. But in general, you can.
That will, yeah.
Yeah.
There'll be other
But
things.
you won't have to fight hard, this follows. Well, actually, you won't have to fight hard at all, because if you take two elements, the product of the determinant is the determinant of the product. And we've just shown that the products are, so there's nothing much to do with these homework problems. It's just making it sound difficult with all our notation. But you have to get used to this notation. We're setting up the language for what we're about to do. You know, what we're about to do is a lot of fun. It's fun stuff, but you just need, think of this as when you before you play a piano piece, you know, the first maybe 6 months, you're practicing scales. So that's what we're doing. In this chapter, we're just practicing scales. We want the language, the vocabulary, the summation convention, all of it to make sense. There's a definition that follows. Again, I'm not writing the full sentence. this is, as you know, is a group in its own right. This is called the Lorentz group. Just simply Lorentz. This is what we're interested in the most. So we just call it, simplified it, called it the Lorentz group. Oh, I like this. I don't know if I talked about this. If you take a rotation matrix, so now I'm just talking for a while before we do a problem. So if you take a rotation matrix, right? And you know R transpose R is equal to what?
R transpose R is just equal to.
Identity.
Yeah, it's just the identity.
Identity. That means each row of the rotation matrix can be thought of as a unit vector that are orthogonal. Instead of writing it as R11, R12, R13, let me call this V1, V2, V3, U1, U2, U3, U3, W. Very good. And if I take the transpose of this and multiply, that means I'm multiplying, the first element would be this times this. So that means V dot V. It'll be 1. If it is V dot U, it's a diagonal matrix, it is 0. So these are all 3 vectors that are unit vectors and they're mutually orthogonal to each other. Correct?
Yeah.
Now, this means R transpose is the inverse of R, which means R is the inverse of R transpose. So I can just as equally say, writing it in the back order, that the columns are also unit vectors that are orthogonal to each other. If you write it out, it will be very clear, but if you want to intuitively think about it, just take a look at the rotation matrix. Cosine alpha, sine alpha, and cosine alpha minus sine alpha, cosine alpha, sine alpha. So it'll be cosine squared plus sine squared, you'll get 1. If you take the other combination, you'll get 0. So a similar relationship is true with Lorentz matrices. And I'll show it. I'll show you one part and I'll ask you to do another part. Except, they're going to be 4, 4. So, and if you take the first row, it'll be a vector of length minus 1. If you take the next 3 rows, you'll get 3 vectors of length 1. And conversely, if you multiply 2 rows, you'll get it to be 0. So let me set this up. So what I'm saying is, there's a simpler, smaller, more friendlier cousin to what we're about to do. So let me state problem 2.11. I won't do problem 2.11 because that's columns. I'll do the other. I don't know which one is which. I'll do the other one as an example. So problem 2.11 says the following. If you have a Lorentz transformation, and if I define a vector T mu to be lambda mu 0, what does that mean? As a vector, the components of T would be lambda 0, 0, lambda 1, 0, lambda 2, 0, and lambda. That's what I mean, right? And then I obviously T for time and X, Y, Z. What do you think X is going to be? Y is going to be what? 2. Z is going to be? And I have used words in here that I haven't defined. because I rearranged my notes and I didn't define these things. But let me define, and again, when I upload it today, I will make sure to move this problem elsewhere or clarify what I mean. What I mean is, you will find that if I do T, T, I will get minus 1. If I do X, X, I would get 1. Y, I would get 1. Z, I would get 1. The definition, I'm going to use some phrase just to, it's coming, it's just, if not today, maybe tomorrow. The language I'll use in the future is, I'll call this guy time-like, if it has a negative length. If it has a positive length, I'll call it space-like. But they're not just they're not just unit vectors in this sense. It's weird, huh? You can have a unit vector of length minus 1, it's still considered unit. It's just minus. But they're also orthogonal. What do I mean by that? If I take any two pairs that are different,
0. So you said you're going to call those, anything that's got a -1 length is time-like?
Negative length is
Negative
time-like.
length. Any negative length.
Yeah, we'll get there. We'll get there. Anything that is a negative length, I'll call it time-like. Anything that is a positive length, I'll call it space-like. Well, guess what? What are the objects of 0 length?
Say again, sorry.
What are the objects of 0 length? I mean, if you have
Time
negative
and space? Space-time?
light-like.
Light-like.
Yeah. Right in between time and space. Like the sandwich. Okay. So that is the homework, but let me get you started. And just to show you a different problem, what I'm going to do is I'm going to define T mu to be lambda 0 mu. So these guys are what? This is actually a column, right? I'm just going to make a row, and I'll show that they are orthogonal. And I'm going to define x, y, and z that way. Yeah, so basically what I mean is time is actually the row this time, lambda 0, 0, lambda 0, 1. That's the first row. Lambda 0, 2, lambda 0, 3.
First column.
That's the first one. And I'm going to, actually first row. First row. And then I'm going to define this to be 0, what is it? 0, 1? No, this is 1, 0, right? 1, 0, lambda 1, 1, lambda 1, 2, lambda 1, 3. What I'll do is I'll show that these guys are, if I take the dot product of this and this, I will show it as 0. You'll repeat something similar for this one. I will use one of the two equations that I wrote on the board there. You will use the other one. So I'm giving you a hint without doing that problem at all. So I'm going to pick, yeah. So mind you, now I'm not showing it, doing any homework problem, but I'm going to show explicitly how this is 0. This is not a homework problem, but it's a clue. So if I take the first two rows of a member of the general homogeneous Lorentz transformation, and if I do this operation on it, I'm going to get 0. Similarly, if I put t and t, what do you expect? Minus 1. X and x will be 1. Okay. Remember, I'm doing one portion of this. You can pick any two pairs and do it exactly the same way. And I'm going to choose one of the two equations I wrote up there. You will choose the other one and show this for, I don't want you to show it for all of them. Show it for one time light, one space light, and one time and space light. Questions before we begin?
The way that you pick which equation you're about to use, it's which index is being consistent, right? So in this case, you would use the upper one.
Very good.
Because it's being summed over.
I'm asking, yeah, because it's being summed over the upper part, right?
Very
So you're
good.
going to use the
Yes.
eta mu
Yeah.
nu on top.
Yeah, very good.
Cool.
Oh. So this is equal to, isn't that true? Ada's diagonal. So then I'm going to, well, you can see now it's a trivial problem. I'm going to pick mu to be 0 alpha. This will be 1 beta. Gosh, it's really not even worth the trouble, is it? So when alpha and beta is 0, I'm going to get minus lambda 0 alpha, lambda 1 beta, plus. Hey, can I do this? Is one up and one down? Yeah. No, I can't, right? I can.
Yeah.
0, 1. Isn't that what the dot product is? The first guy is minus. Oh, wait a minute. So I should write it as 0, 1, 1, 1. 0, 2. Should I just write it out?
Why does it flip to negative when alpha and beta equals 0?
Because eta alpha beta is, what is eta 0, 0? I mean, so eta mu nu is this matrix.
Okay.
So when mu and nu is 0, it's minus 1. Well,
Okay.
here I picked 0, 1, which means I picked this guy over here. Right? So that's why it's 0. And then I'm going to sum alpha and beta through all numbers, right? So first I pick 0, it's diagonal. So the only choices I have is 0, 0, 1, 1, 2, 2, 3, 3. But when I pick 0, 0, that is alpha 0, beta 0, I get eta of 0, 0. And 0, 0 is minus 1.
And that's what keeps time positive. essentially.
That's what keeps time, well, negative in some, well, but we haven't talked about how to deal with time.
Alright.
I have a question real quick.
Yeah.
On an exam,
Yeah.
would you take off points if instead of doing it the algebraic way, we did it
Yeah.
the matrix way?
By matrix way, what do you mean?
Like do matrix math instead
there's a lot
of
of
doing them together? It is a lot of math, but like, just in case, we're gonna have notes.
Well, he means like getting rid of the Einstein convention.
Yeah,
Straight up doing
instead of
that.
doing-
Oh,
Einstein
no,
convention,
I want you to
matrix.
use Einstein convention. Submit
Okay.
to Einstein.
Okay, okay. All right, so no matrix multiplication.
Yeah,
Just do Einstein.
yeah, you're gonna, I'm trying to avoid pain.
Because it will, it is quicker. It is legitimately quicker. I can see that.
Unless it's the rotation.
Did you just say
right? Then you would need to do.
legitimately?
Well, I mean, if you have to use summation convention for things like this, you can, and you may have to.
Yeah.
But otherwise, things like this are called covariant equations. So we're looking for covariant equations. The general theory of relativity, it's called general covariance. You can use any coordinate system you want.
I feel like eventually the matrix system.
It will
like,
just fail. It will
Yeah.
just fail.
Well, can you even use this for like rotation?
Sure, sure.
As long
You
as
just
you
have to know what the matrix.
Yeah,
is.
so except in rotation case, the rows and columns are unit vectors, but it's a regular dot product. Here too, they are unit vectors, but it's not the regular dot product, it's that weird eta dot product. Yeah, so what I've shown is the rows are unit vectors. The first one has length -1, the next 3 rows have length 1. Same way the columns. First column has length -1, That's what you do in your homework. The 3 columns will have length 1. And if you take 2 columns, 2 different columns, and you do the inner product, you'll get 0. 2 rows, and you do the inner product, you'll get 0. Okay? So this should serve as a template for that problem. I might ask you to construct a particular Lorentz transformation from a previous problem, and then I'll ask you to show that the rows form a unit orthonormal set of vectors. We have to define what it means for orthonormal. We'll allow -1 to be included. As long as the number is 1, we'll include it. Yeah? Actually, that's a good place to start.
And